Welcome back. In this video, we look at a really interesting NLP technique called topic modeling. The scenario is that we have a corpus of documents. What are the topics in this corpus? That is, what is this corpus about? And which topics are found in individual documents? In other words, what is this particular document about? We have seen how TF-IDF can identify keywords that are representative of a document. Topic modeling is an alternative technique. This diagram gives an intuitive explanation of what topic modeling does. The diagram is from an ACM article by David Bly, and I have a link to the article in the chapter. In this diagram, 4 topics are identified, represented here by 4 colors. And you see that topics are really words. So here, let's look for yellow topics. Different words represent the yellow topics. This topic, that is a set of words, technically is a multinomial distribution over words. And then a document can be represented by a distribution of topics. Over here we see the distribution of topics for this particular document. The most common topic modeling approach is to use latent Dirichlet allocation, LDA. LDA is considered to be a generative probabilistic model with both observed and hidden variables. The observed variables are the words, and the hidden variables are the topics. The observed and hidden variables combine in a joint probability distribution. But first of all, what is a Dirichlet distribution? Here we have a multinomial distribution. We have 3 possible outcomes, and there's different probabilities associated with each outcome. We could express that like this. A Dirichlet distribution samples over multinomial distributions. It's often called the conjugate prior of multinomial distributions. Here's some diagrams to illustrate the Dirichlet distribution. In our context, we're going to consider the topic to be a distribution over words. Here's a very unwieldy mathematical expression of LDA. And here's a graphical representation. Let's look at the graphical representation first. The shaded area is the observed data, the words. Unshaded nodes are hidden variables. Our hidden variables are topic proportions for each topic in each document, topic assignments for a given document, and the topics themselves. Plate N here represents collections of words within a document. Plate D represents the collection of documents in the corpus. Plate K over here represents the topics. This alpha hyperparameter will control document topic density. The higher the alpha, the higher the number of topics assigned to each document. The eta hyperparameter over here represents topic word density. The higher this value, the more words per topic. Now let's take a look at this mathematical expression. The probability of our topics, topic proportions, topic assignments, given the words in a document, can be represented by this joint probability. Calculating this joint probability would be intractable, so a sampling technique is used. Gibbs sampling is often used, which is a Monte Carlo Markov chain technique. Let's back up and revisit Markov chain Monte Carlo methods. Let's say we don't know any statistical parameters about height of people in a given population. What we could do is just randomly sample them. And by the effect of randomly sampling, we'll find the distribution. Gibbs sampling is a more complex version of this, where we start with many variables at random values. And then iteratively, we hold all variables constant but one and repeatedly sample the data to get the best estimate of that variable. That process will be repeated for each variable over hundreds or thousands of iterations until convergence, until the parameters stabilize. Let's look at how to do topic modeling with the Ginsen package, which we've talked about before. Gensim actually has two topic modeling algorithms, LDA and LSI. We're going to use our same corpus here. This time, not dividing the documents, we just have 4 documents. And we'll look at part of each document. Here are the imports that I'm going to need. I established the number of topics as 8. This is one of the most important but most challenging parameters that you set. My thinking at the time was that I had 4 very different documents, and they're bound to be at least 2 topics in each document. So I arbitrarily came up with this number of 8. I'm doing some pre-processing, basically removing non-alpha tokens and removing stop words. After pre-processing for each of the 4 documents, we see the first 5 words. This function from gensim will map words to ID numbers. We see the length of the dictionary here is a bit over 4,000, and here are some of the items. Next, we build a corpus using the gensim function doc to bag of words, and let's print out a little bit of the corpus. And we see our dictionary. What this is showing is that for document 0, word 4, which is accelerator, occurred 0 times. Word 2, which is absorbed, occurred 1 time, and so forth. This is just a little bit of a sanity check to see that all of these gensim functions really are doing something meaningful. Now let's build the LDA model, giving it our corpus, our number of topics, and the dictionary. Printing out the results, let's show the topic. I asked for 8 topics, so here they are. I'm printing out the top 10 words associated with that topic, along with an importance factor. Something I see right off the bat that disturbs me is that inflation appeared in a lot of the topics when I know that it only occurred in one of the documents. Let's look through the topics again and look at the top words. This is a little bit of a cleaner look. Topic 6 here looks fairly cohesive. These words clearly came from the anatomy chapter, except for islands and inflation. So I'm seeing some things that concern me here. In order to analyze further, we can export top 10 words from a given topic. And there's a built-in metric we can use, coherence. Coherence is a variation of PMI, point-wise mutual information. For coherence, we want to see a metric above 0.5. It ranges from 0 to 1. The closer to 1, the better. Above 0.8 is considered very, very good. So we did not build a good model here. There is a nice visualization here that you can install this package with pip or pip3 and then run the visualization like this. This is a really nice visualization. On the left, these numbers indicate the topics, 1 through 8. Significant topics are shown in balloons. So what we want to see is no overlap, and we don't want to see balloons that are too close together. When you hover over a balloon, you get on the right, the most relevant terms. So for topic 3, topic 1. So now we've seen by 3 different methods that our topic model is actually not very good. We've seen that by visually inspecting the words in the topics. We've seen that by this visualization here. And we've seen that by the coherence metric that we got, well below 0.5. All of these things taken together tell us that the number of topics is too large. I ran the topic modeling again, this time with the number of topics set to 4. So I have 4 numbers here. And the coherence score went up very slightly, but it's still bad. And we see that there's a lot of overlap here in the words. Inflation occurs in both topic 1 and 2. Topic 3 actually looks pretty good. I played with a few of the other options that you can get in the documentation, and there's quite a few parameters you could play with. Some of these, the alpha and eta, refer to the hyperparameters that we looked at. I tried different values and didn't get very good results. And the reason we're not getting good results is that LDA is very hungry for data. And this example used a tiny corpus of just 4 documents, and that's the reason we didn't get very impressive results. The algorithm really needs to see words that co-occur together in many different instances to learn that they're related. Let's look briefly at the other method that Ginsen provides, which is LSI. LSI, latent semantic indexing, also called LSA, latent semantic analysis, it's a dimensionality reduction technique. It will essentially reduce similar words to the same index. LSI will, in general, be faster to train, but LDA can get better results provided that we have a significant enough corpus. All right, let's try LSI. And we see that we got a decent coherence score, even on this tiny corpus. So if you have a smaller corpus, LSI might be a better approach. But if you have a significant corpus and you want really good results, you should stick with LDA. How useful is topic modeling? That's an open question. I have used it in a question generation system that I developed with pretty good results. But it took a lot of fiddling, and the results needed human supervision to assess the validity. There are industrial applications of topic models in bioinformatics, document retrieval and clustering, and much more. Given our not so exciting results, I'll leave you with this quote from British statistician George Box. All models are wrong, but some are useful.